Welcome to my second video for Physics 114, where I'm continuing my attempt to apply principles of introductory physics to my everyday activities. Now, in my previous video, I discussed patterns of motion that I use in training my clients. In this video, I intend to show how Newton's laws of motion make my own workouts more impactful. The reason for this is that Newton's laws describe the relationship between a body and the forces acting upon it, and its motion in response to those forces. I thought, so what better place to illustrate those responses than in the gym? And I think that gaining a clearer understanding of the specific forces enhance the difficulty of the exercise routine, which then overall increases the efficacy of the program. So yeah, let's head on in and see what we can observe from Newton's point of view. Before we jump into examples, let's briefly discuss force. First, we have the force of gravity. The gravitational force between an object of mass and Earth is the object's weight. Its weight is the force exerted on the object in a gravitational field, and this always points downward. Secondly, we have normal force, which is exerted by a surface on an object and is pointed perpendicular to that surface. Next, we have tension, and this force can only pull and applies to ropes, strings, and chains, helping to keep an object on a particular trajectory and is directed along the axis of an object. Next is spring force, and this is entirely dependent on the material and is a force exerted by a compressed or stretched spring upon any object attached to it. An object that compresses or stretches a spring is always acted upon by a force that restores it to rest or its equilibrium position. And next we have friction, a force that occurs between surfaces and runs parallel to those surfaces that resist sliding across one another. Within the friction force, we have kinetic friction, which pertains to friction during motion, and static friction, which occurs before motion. Let's take a look at how these forces present themselves in Newton's laws of motion. Newton's first law of motion states that a body either remains at rest or continues to move at a constant velocity unless acted upon by an unbalanced force. This means that all force vectors acting upon an object must equal 0 to indicate at rest or moving at constant acceleration. If the force vectors do not equal 0, then the object will indeed have acceleration. So in class, we were given the example of a chair sitting on the classroom floor. There's the chair and the floor. So the object of interest is the chair. Here's our particle and our x-axis and the y-axis. And the forces acting on the chair are the force of gravity and the normal force exerted upward by the floor. These vectors are of equal magnitude and cancel, thus indicating at rest. So the in-class example for constant acceleration was a chair being pushed horizontally and moving at a constant speed. So we have the chair as a particle, and again we have the x-axis and our
Let's take a look at how the
y-axis.
first law translates to the gym.
And we have the force vectors of Fg and our normal force.
In this example of the
which
Swiss ball
cancel.
pike, I've upset the balance forces previously
And
shown
the
by introducing
force
static friction, which the ball experiences on the
of
floor
being
prior to
pushed.
motion, kinetic friction on the carpet as
And
soon as
because
the
it's
force of my
moving
feet and
along
legs
the
pulling the
floor,
ball
we
overrides
have
the static
the
friction
force
threshold
of
and
kinetic
pulls it toward my
friction
head.
as well.
And of course the force
And
of the pulling motion
because
itself.
it says that
These
the
override
chair
the
is
balance
moving
forces,
at a
ultimately
constant
causing
speed,
acceleration of the
we
ball.
have zero acceleration, and thus
Newton's
we
second
know
law of motion states that an
everything
object with mass
cancels.
will undergo acceleration where the net force is a vector sum of all individual forces acting on an object in the same direction as the net force and inversely related to the mass of the object.
Put more simply, when there is a net force on an object, acceleration goes in the same direction of that net force. More force means more acceleration, and more mass means less acceleration. Our in-class experiment consisted of pulling one classmate in an office chair down the hall by a rope with a luggage scale attached to it and monitoring the force to keep the scale at 15 pounds. We noticed that the amount of acceleration needed to maintain that at 15 pounds was much higher than the acceleration needed to maintain that same 15 poundage when we piled classmates on the chair and increased the mass. We were asked to experiment with a simulation in which we could observe Newton's second law at work. Here we can see an example of 55 newtons of force applied to a 50 kilogram box. After 15 seconds, speed accelerates 19.5 meters per second. When the same 55 newtons of force is then applied to a 200 kilogram refrigerator, speed accelerates at a much more reduced rate to 5.9 meters per second after 15 seconds. Here I'm performing a pull-up with an assisted weight platform. I weigh roughly 100 pounds and the counterbalance weight is set to 80 pounds, resulting in my pulling up 70 pounds of weight. I can easily rep out 10 pull-ups very quick, implementing a strong force. This time I'm without the assisted weight platform, pulling up my body weight. The acceleration of my noticeably slower due to the increased mass I'm responsible for pulling upward, but I'm also putting more weight on the bar here. To hang, I put force on the bar and the bar puts the same force on me, so they cancel and I don't move anywhere. But in order to move upward at some acceleration, I need force to equal mass times acceleration. Finally, we have Newton's third law of motion, commonly referred to as the law of reaction. Applied force is met with an equal and opposite reaction.
We're at rest. Okay, Lindsay, walk. Read, what years is that?
20-ish.
Same.
In fitness, that every action has an equal and opposite reaction, prominently to impact forces. As seen here, when I kick up into a handstand push-up and land, I exert a force on the ground. It exerts that same force back up at me, which must dissipate through the shock absorbers, the joint bursa in my elbow. This happens again to the floor and land, and the ground force is then dissipated through the meniscus in my knee. In addition, the whole idea of strength is that you create sudden adaptations of imposed demand, meaning if you apply a specific force to the body and challenge it, it will adapt, which may oversimplify, but definitely encompasses the concept of Newton's third law. So I just finished my workout for the day, and I was going to do my final thought in the gym, but there were too many people, and I wanted to be able to reflect openly about this project. And what I noticed through this quarter and this project in particular is that there's more application for physics in my daily life than any other subject. And Newton's laws are extremely important in a fundamental sense in the fitness world, because a body in motion stays in motion, and we need a net force to generate acceleration in any exercise. And each force implemented on the body creates an equal and opposite force, which results in overall advancements in physical fitness. So, yeah. Thanks, Newton, for establishing the foundation for exercise science. Thanks for watching.